this symbol and this symbol. What do those symbols mean? It means take the antiderivative, right? How is it different if there are numbers here and here? That means find the area. But this just means, without numbers, means just take the antiderivative. And it's called an indefinite integral. Okay, so we're going to take the antiderivative of this. So we're going to do this two different ways. And we've been doing problems like this. Why is this kind of a tough antiderivative? Because it's a chain rule problem. There's a whole mess to the 1/2 power. So when we take the antiderivative, we can add 1 to the exponent and divide by the exponent, divide by 3/2, but that's the same as times n by 2/3, right? And then this is pretty close to the right answer, but the problem is if you took the derivative of this, an extra 2 would pop out. That's not here. So how do you get rid of that extra 2? Times by 1/2 or divide by it or whatever, right? So if you times by an extra 1/2, then you have the correct answer. So we've been doing backwards chain rule problems like this, where you logic it out and just multiply by the 1/2. Then the final answer, the 2's would cancel, right? It would be 1/3 times 2x plus 1 to the 3/2 plus c. Okay, but there are some antiderivative problems that are harder than this. And so we need a method that's going to help us with those harder problems. But I'm going to start by doing this problem with that method. Okay, so this method is called U substitution. So we know how to do this antiderivative. It's not too bad, but we're going to do it in a different way now, a method called U substitution. And then we're going to use this U substitution method on harder ones, on harder antiderivatives. Okay, so what you do is you make U equal to the inside function. So the function that's being raised to the 1/2 power is 2x plus 1. So that's what you let U equal. Okay, then you take the derivative of that. We kind of said this out loud earlier, right? We said, okay, yeah, but there's an inside function, and the derivative of that is 2. Okay, then you write down what the differential is. Remember, this is called the differential. It's been a long time since we've said that. It was before Christmas. This is called the differential. And then you solve for the dx. Okay, so the reason we're doing all of this is we want to take this problem, which is sort of hard, and transform it into an easier problem. So since U equals 2x plus 1, this is U to the 1/2 power, right? So I'm going to rewrite my original antiderivative, but instead of 2x plus 1 to the 1/2 power, I have U to the 1/2 power. So I'm just replacing the 2x plus 1 with U. And then I still have a dx over there, right? But so I'm going to replace dx with this, du over 2. So I'm just substituting in. That's why it's called substitution. And I'm using the variable u, so that's why it's called u substitution. All right, so here's my antiderivative that I've got now. And now I'm just going to take the antiderivative. So you just bring the 1/2 down. add 1 to the exponent, divide by the new exponent, divide by 3/2, right? AKA multiply by 2/3. So then that's 1/3. And then I can translate back to x's. Instead of u to the 3/2 plus 1, instead of u to the 3/2, I have 2x plus 1 to the 3/2. Okay, so that was writing down a lot of stuff, and it was kind of unnecessary on this problem. But I did it on this problem to show you that you could write it down like that, and you'd still get the same answer as what we got when we logicked it out. Okay, so there's this new method called use substitution, and the substitution. And the purpose of use substitution is it is a method used to make tough antiderivative problems easier. Use substitution is a method used to make tough antiderivative problems easier. So maybe example 0 wasn't tough for you, and then that means you didn't need this method. You could just logic out, hey, I see an extra 2 is going to pop out, so I need to compensate with the 1/2. And that would be totally fine. But now we're going to do some harder ones where you're probably going to need use substitution because they're harder than that one. Okay, so the next one is the antiderivative of x cubed plus x squared plus 5x to the 5th power times 3x squared plus 2x plus 5 dx. Okay, so this looks like a pretty tough antiderivative problem. So we're going to do use substitution on it to try to make it easier. So this is not always true, but a general rule is that u should be the inside function. So what's the inside function on this problem? X cubed plus x squared plus 5x, right? Because that's being raised to the 5th power. So since x cubed plus x squared plus 5x is inside of the 5th power, that's why we're letting u equal that. Okay, then you find the differential. I could have written down du dx equals 3x squared plus 2x plus 5, right? But I just skipped that step. I went straight to the differential instead of to the derivative in the middle. And then you solve that for dx. So dx is du over that whole big mess. Dx is du divided by 3x squared plus 2x plus 5. So now I take this problem here, which was tough, and I'm rewriting it. So instead of the antiderivative of a mess to the fifth power, I have the antiderivative of u to the fifth power. And then I'm still stuck with, so I replaced this with u to the fifth, right? Now I'm going to recopy that. So I've taken account for that and this, but I haven't written this down yet, right? But this can be replaced with that. And then George says, okay, that's good. Why is that good, George? Because now that's going to cross out with that, right? So I've got the antiderivative of u to the fifth du. So the purpose of u substitution is to transform a tough antiderivative problem into an easier antiderivative problem. And this antiderivative looks much easier than that one did, right? So in this case, the u substitution was successful because I've got an easier antiderivative problem. Now, what people forget is, now we're supposed to take the antiderivative. The whole purpose was to find the antiderivative, right? So I've got my easy antiderivative problem, so now I should do that problem. That's u to the sixth over sixth plus c. So now I have my antiderivative. But the original problem had x's in it, so my final answer should have x's in it. So for my final answer, I'm going to write 1/6. That was u to the sixth, but u is x cubed plus x squared plus 5x. So then that's my antiderivative. So how can I check to see if this is the correct antiderivative? Take the derivative of it, right? When the 6 would come out front, and 6 times 1/6 is 1, then it would be this to the fifth power, but then times the derivative of the inside, 3x squared plus 2x plus 5, right? Ah, it is that. So I got the right answer. If this is the correct antiderivative for that, then the derivative of this should be that. And it is. Okay, let's try. Got a bunch more to try. This is a method, so we just have to practice it. So for example 2, I've got the antiderivative of s to the 1/3 times the cosine of s to the 4/3 minus 8. So what do you think u should be? S to the 4/3 minus 8, right? Because that's sitting inside of cosine. Remember, the general rule is u is the inside function. So since it's the cosine of that mess, that's what u is. Yeah.
Since you keep saying that that's the general rule, so is there any...
I'm just, yeah, that's why I keep saying that, because it's not always going to be the case. But for now, let's hold fast to that, and then we'll look at some exceptions later. Okay, so then the derivative of this, the differential, is 4/3 s to the 1/3. Then I need to solve that for ds. So I'm going to divide by 4/3. That's the same as multiplying by 3/4. And I'm going to divide by s to the 1/3. So now I can translate. I'm going to take this problem and transform it into hopefully an easier antiderivative. So the s to the 1/3, I'm not sure what that is, so I'm just going to recopy that. Then I have cosine of a mess, but the mess is u, so that's the cosine of u. So I've accounted for this, I've accounted for this. I still have to write ds down, right? But this whole mess is ds. So 3/4 times du over s to the 1/3. And then that's good news, right? Because that and that are going to cross out. So I've got the antiderivative of 3/4 cosine of u. So the purpose of u substitution is to transform a tough antiderivative problem into an easier antiderivative problem, and I was successful with that here. This is an easier antiderivative. So now I'm going to go ahead and take the antiderivative, since I've got one that I can deal with. 3/4 is just hanging out, it's just a constant. Antiderivative cosine is sine. And then the last step is, u was just a temporary variable that we were using for our purposes, right? To just temporarily we had u be something, so we could get an easier problem. But the final answer shouldn't have a u in it, because the original problem had nothing to do with u. So it's 3/4 times the sine of s to the 4/3 minus 8. Is everybody doing okay? Are you doing okay with you? I'm always worried that an English teacher is going to walk by right when I say, "What should you be?" And they'll think, "What's he talking about? This is not supposed to be a philosophy class." And then I say, "You is," and they're like, the English teacher's like, "He's saying you is." I mean, I knew he was a math teacher, but you would think he could say that correctly. It should be you are, right? Anyway, I told these jokes last year too, right? You don't remember anything except that.
Oh, yeah.
Sorry about that. So now you'll be distracted the rest of the class. Whenever I say you is, you'll be distracted. Don't be. Think about the calculus. All right, so we're on to example 3 now, I guess. Ah, yes, this is a good one. Antiderivative of the square root of the cotangent of x times the cosecant squared of x dx. Okay, so this one's a little bit awkward because there's two inside functions. Cotangent is sitting inside of the square root, and cosecant is sitting inside of squared. So I'm just going to pick u to be cosecant. It's a reasonable choice because the cosecant is being squared. So that is an inside function. Write this down, we'll see what happens. Okay, so then you take the derivative of that, right? The derivative of cosecant is negative cosecant times cotangent. Then you have to solve for dx, right? So you divide that to the other side. Okay, so then you've got the antiderivative of the square root of cotangent of x. I'm stuck with that. But then this is u squared, so that's nicer, less messy. And then dx is that whole mess, right? du over negative cosecant x times cotangent x. And then that's pretty much it, right? What's the purpose of u substitution? Take a tough antiderivative and make it easier. Is this one easier than that one? So u substitution is not fulfilling its purpose here. So that means I picked the wrong u. It was reasonable to pick u equal cosecant because that was being squared. But it's also it would also be reasonable to pick u equal to cotangent of x, right? Because that's being square rooted. Okay, so what's going to happen is you're going to sometimes pick the wrong u. And you'll know that you picked the wrong u when you get to this stage and you've got a tougher antiderivative than you started with. The whole purpose of u substitution is to give you an easier antiderivative, but it's not coming out easier, so then you know you're on the wrong track. I wish I had better advice than that, but I don't. You just have to pick one and hope that it makes it easier. Sometimes the choice is clear. On the first three problems, I think the choice was clear, but on this one, the choice wasn't clear. Okay, so anyway, so we figured out cosecant wasn't right, so now we're going to have u be cotangent, and the differential for that is negative cosecant squared. So then you divide that to the other side. So then translating again, I've got the antiderivative of the square root of cotangent. So that's the square root of u, which is u to the 1/2. Cosecant squared is still there for now. But then dx is du over negative cosecant squared. So then that's nice, right? Because those are going to cross out. So my antiderivative is negative u to the 1/2 du. So this antiderivative is definitely easier than the original one. So now we know we picked the right u. So now we're prepared to take the antiderivative. Sometimes you forget that. You do all this work and transform it, but then the purpose was so you could take the antiderivative. So take the antiderivative. So negative's just hanging out. Add 1 to the exponent. Divide by 3/2, aka multiply by 2/3. And then the last step is to translate back to x's. U was just a temporary variable for our convenience. But we need to give the final answer in terms of x's. So negative 2/3 times cotangent of x to the 3/2 plus c is the final answer. Is everybody doing okay? All right. Yes, Dan.
I'm wondering, like, with the derivatives of like the cotangent and the cosecant, is there somewhere in the book where we can find those derivatives? Because I've been having to like look them up on Google. Like I don't know how you're supposed where you would find those.
Yeah, I mean, they're in your notes, and they're not, section 3.5 is where all the trig derivatives are. But by now, you should have them memorized, because it's been months and months and months, so. You just got 2 months left. You've had 4, so I'm starting to get worried. All right, so this one is going against the general trend. So I stated that u should be the inside function, usually. And that has been the case on the first 5 problems, 4 problems. But here, there's no inside function. So sometimes u substitution can be used even when it's not a chain rule problem. And this is an example of that. Okay, so what you can pick u to be is x squared plus 1. So like I said, u is usually the inside function, but that's not happening on this problem. In this case, u is just the bottom of the fraction. Yes, so it is sort of a chain rule problem, as Matt is pointing out to us. Very nice observation. What he's saying is x squared plus 1 is being raised to the negative first, and then it's being times by x. So yes, nice thinking. Mm-hmm.
If you don't mind me asking a question about number 3.
I don't mind.
So why weren't we able to do something along the lines of like having like a U and like let's say Q and just using both of them?
I think that's possible, yeah.
Is it just more challenging?
I guess my answer to that would be, in this case, I didn't need another variable, so it worked out pretty well just with u. So I'm fine with that, but if you can come up, I'm not saying it's not possible to do it some way that you're thinking. So it'd be good to investigate that. That's a good thought. All right, so if u equals this, then du equals 2x dx. So then you divide the 2x to the other side, so dx equals du over 2x. So then this translates into the antiderivative of x over u and then dx is du over 2x. So then the x's cross out. So we have the antiderivative of 1/2 times 1 over u du. So then when you take an antiderivative, a constant can just move down. What's the antiderivative of 1 over u? Nice job remembering the absolute values. It's the natural log of the absolute value of u. And then you translate back to x's, so it's 1/2 times the ln of the absolute value of x squared plus 1 plus c. Everybody okay? Matt, that was a really nice thought that you had, by the way. Okay. I know I said it the first time, but I want to make sure you realize that was really good thinking. Yeah. All right, so example 5 is integral of that's what example 5 is. Okay, the first thing that bothers people is they don't like that dx on top of the fraction. And I can understand why. It just means this. So what we're taking the antiderivative of is this function. And then fancy mathematicians get cute and write it like that. You can understand how they could see that it maybe should be like that. Anyway, try to get used to it because you might see it. Okay, so again, this is one of those U substitution problems where there's not an inside function. So what should U be? So there's two choices. There's either x or there's ln of x. If you let u equal x, it's pretty uninteresting because then there's a u there, there's a u there, and there's a u there, and it's the exact same problem. So u equal x is a good knee-jerk choice, but then after I say that, you can see that doesn't really do anything. Okay, so then u should be the ln of x. So then du is 1 over x dx. So then dx is x du. So now translating, we got the integral of 1 over x times u and then dx is x du. So that's nice because the x's cancel. So what's the antiderivative of 1 over u? Natural log of the absolute value of u. So then when you translate back, it looks really weird. Natural log of the absolute value of the natural log of x plus c. People are like, whoa. One natural log is bad enough. Why would I want two in the same problem? It just means take the natural log of whatever x is, then take the absolute value of it, and then take the natural log of that. That's all that means. Not that big a deal. but it doesn't look very pretty because you don't like natural logs as they are. So 2 of them, yeah, I can sympathize. Everybody still doing okay? So what's the purpose of U substitution? To make tough problems easier. To make tough what kind of problems? Antiderivative problems. So if you're on a test and you've got an antiderivative, maybe U substitution is the way to go. Maybe not, though. It may not say use U substitution. It might just have an antiderivative down there, and you got to decide, right? Okay, so we did a bunch of hard ones. Now I want to go back quickly just to 2 easy ones. So ones that we already knew how to do before today. So this is example 6, and it's the antiderivative of the secant squared of 4x plus 2. So if you were going to use U substitution, what would U equal? 4x plus 2, right? Because that's the inside function. But the derivative of the inside is just plain 4. So we should be able to do this without writing down all the U's. I'm not saying that if you want to write down what U equals and do it that way, fabulous. But it would be nice to just say, hey, the antiderivative of secant squared is tangent, because the derivative of tangent is secant squared, right? And then, okay, this is pretty close to the right answer, because the derivative of this would be secant squared of 4x plus 2, except if I took the derivative of this, an extra 4 would pop out. So I need to compensate for that by multiplying by 1/4. So it is totally fine if you do this problem, writing down U equals 4x plus 2, doing all that stuff. Totally fine if you do that. I'm just saying for some of these easier problems, maybe you don't have to do that. But maybe it depends on what time it is, how much sleep you got the day before, etc. But if you don't have to write it down, don't waste the time on the ink. That's all I'm saying. So let's try one more. How about the antiderivative of e to the pi over 4t dt? That's e to the pi over 4t power. So if you were going to write down what u was, what would u be? Pi over 4t, right? Because e is being raised to that power, so that's the inside function. I'll probably do that problem that way in just a second. So u would be pi over 4t. But if you just were going to logic it out, the antiderivative of e to something is e to the something, right? Antiderivative of e to the x, well, the derivative of e to the x is e to the x, so the antiderivative of e to the x is e to the x. So the antiderivative of e to that is e to that, except there'd be a little bit of a chain rule, right? If you took the derivative of this, an extra pi over 4 would pop out. So you have to compensate by multiplying by 4 over pi. So that was method 1. Just logic it out. If you've gotten a lot of sleep and you're thinking sharply, right? But if you're not thinking sharply, you can always put down u equals pi over 4t. So du is pi over 4 dt. So dt is 4 over pi du, right? Dividing that over. So then you translate, that's the antiderivative of e to the u times 4 over pi du, right? So now we're prepared to take the antiderivative. This is just a constant, so it could come out in front of the antiderivative. Antiderivative of e to the u is e to the u. And then you translate back. So you get the same answer. Writing down a lot more stuff, right? So senior year is stressful enough as it is, right? Everybody's asking you, what do you want to be when you grow up? What should you be? And now I'm asking the same question. What should you be? You're tired of this question. Sorry.